Nature of Matter Elements, Compounds, and Mixtures, Chapter 8. Have you ever wondered what the world around you is made of? Look around the staircase you use, the air you breathe, the water in your bottle, the food in your lunchbox, the clothes and shoes you wear, the book you read, and the trees outside, the ball you play with, and even the stick you carry. All of these are examples of matter. So, the staircase, the air, these are air particles, water, and books, book, trees, all of them are made of matter. They all are matter. Matter is things that we can that has a mass. So these all have mass. Has some mass. Air also has some mass. Its weight is not zero. Water has some mass. Book has some mass. Tree has some mass. And you have learned in earlier grades. You have also learned that these all things are made up of tiny particles. Most of the things around us are not made of just one substance. Rather, they are made up of two or more substances. So, many things around us, like trees, so they do not contain any one substance, like they do not only contain oxygen, they also contain particles of carbon, some particles of water and many different particles that together constitute the tree. They're made up of two or more substances mixed together. Now let us now understand how different substances come together to form mixtures. What are mixtures? Have you ever wondered what makes your poha so delicious or how to make perfect sprout salad? While these dishes may seem very different, these two are very different. They share something in common. These two have something in common, and that is that they are made by mixing several ingredients. In poha, you can see some peanuts, some chilies, some and lemon, and the main poha. And in sprout salad, you can see sprouts, some tomatoes, and carrots. We observe the mixing of substances in everyday life. Sugar dissolved in water is also a mixture. So if we dissolve some sugar in water, it is also a mixture. And so are soups and lemonade. They are also mixtures. When two or more substances are mixed where each substance retains its properties, it is called a mixture. The individual substances that make up a mixture are called its components. The components of a mixture do not react chemically with each other. So the components of the mixture will not react chemically. So, for example, if we have peanuts and chilies, if we keep them side by side, these are chilies and these are peanuts, they will not react. They will just stay there forever. In some mixtures, the components like green gram, chickpeas, onion, and tomato in a sprout salad are easy to see. Such mixtures where different components are generally visible with the naked eye or a magnifying device are non-uniform. So, for example, we have put some sand in water. We can see it with our naked eyes that there is sand in the water. So we can say that this is a non-uniform mixture. And there are also other examples that we will see see later. On the other hand, some mixtures have components that cannot be seen separately even with the help of a microscope. For example, if you mix sugar and water, they will form a uniform mixture and we cannot see it individually like wow, this is water inside and these are sugar particles. No, we cannot see like this. We will only see it like this. Such types of mixtures where the components are evenly distributed and cannot be distinguished are uniform in nature. So this is a uniform mixture. Uniform mixture. Do you know that stainless steel is also a mixture? Stainless steel contains iron, nickel, chromium, and a small amount of carbon. So these plates, everything that are made of stainless steel are have so they have iron inside. Iron. Then they also have nickel inside. They are also used in coins, and then chromium. They have all of these things inside of them, and they even have some carbon inside. These are carbon, some carbon also. They are mixed so uniformly that the entire mixture appears the same throughout and one cannot see the individual substances. So imagine that we have a plate, we cannot see that. Here we can see that, or that is I can see some iron, I can see some carbon, I can see nickel here. No, that is not how it works. We will see all of them as just one. Such mixtures are known as alloys. So these are all made of alloys. Brass, a mixture of copper and zinc, and bronze, a mixture of copper and tin, are some other examples of alloys. So these all are alloys. Our scientific heritage. Mishra Loha was given the name to a mixture of two or more metals. They are like alloys. Distinct from its constituent metals, ancient Indian texts such as Charak Samhita, Susrit Samhita, and Rasratna Samuchaya, Rasjal Nidhi, etc. mention the use of alloys. They all use alloys for medicinal purposes. People used to consume these. For example, bronze, also known as kamsya, is an alloy made up of copper and tin. Was used to improve digestion and boost immunity. Is air a mixture? In Curiosity Grade 6, you learned that about air and its composition in the chapter Nature's Treasures. Is air a mixture? What kind of mixture it is? It so air is a uniform mixture. It is a uniform mixture. Why is it uniform? Because we cannot see. Imagine that there is air in front of you. You cannot tell that I can see nitrogen over here, some nitrogen over here. I can see some oxygen. I can see some oxygen here. No, we cannot see. We can just say tell that there are air. Nitrogen, oxygen, argon, carbon dioxide, and water vapor. Out of these, oxygen is required by most of the living beings. So, air contains nitrogen, oxygen, argon, carbon dioxide, and water vapor, and they can. So, and oxygen is the most required by the living beings to stay alive. It also helps in combustion. Oxygen is also important for combustion combustion because what They need it for combustion. Nitrogen, which constitute about 78% of the air, does not take part in combustion. So nitrogen is usually seen as very useless in the air, even though we have the most of nitrogen here. We also learned that air has water vapor in it. When warm air touches a cool surface, the water vapor turns into liquid water, forming tiny droplets. Recall the experiment where you tested the presence of carbon dioxide in the air we exhale. Let us confirm the presence of carbon dioxide in the air. So we will look at the following activity that will help us to tell that there is carbon dioxide in the air. So we need to perform these steps carefully. Take a glass tumbler and fill it half with water. So we need to take a glass tumbler and fill it half with water. We have filled it with water. Add a small amount of calcium oxide slowly to it. So we add some calcium oxide, quick lime to it. What do you observe? It, it reacts vigorously with the water to form calcium hydroxide, and it also releases heat. We will feel some heat there. Stir continuously to make a solution of calcium hydroxide. We have now, after the reaction that we have done above, now we have formed calcium hydroxide. This is called lime water. Filter it and observe its color. So this is lime water. It's used mostly colorless. Leave the colorless solution in a petri dish for a few hours. You need to leave it for a few hours. So after leaving it for 3 to 4 hours, let's see what happens. And keep stirring the solution at regular intervals. In these 3 to 4 hours, every 30 minutes or so, we need to stir it. What do you observe? It does it turn milky? So yes, we can see that it has now turned into a milky solution here. It looks now very white. Can you explain why the solution has turned milky? You know that when lime water turns milky, when carbon dioxide reacts with calcium hydroxide. So it has turned milky because it has reacted with calcium hydroxide to form calcium carbonate and water. Since lime turns milky when exposed to air, this activity demonstrates the presence of carbon dioxide in the air. Calcium hydroxide, calcium hydroxide plus carbon dioxide is equal to, it makes, not equal to, calcium carbonate plus water. So this, after this reaction, it has formed calcium carbonate, and it is also contains some water inside. Apart from these gases, have you observed anything else present in the air? Have you ever noticed tiny shiny particles moving in a beam of sunlight? So we have seen dust particles. Dust particles. Usually what happens that if there is a window and light is coming out, we can see some shiny particles like this, which are actually dust, which is dust. Apart from these gases, so let us explore now. We will see this presence of dust. Take a black sheet of paper. Ensure that it is free from any visible dust particles. Place the black sheet of paper undisturbed near an open window, so you can see it near the open window or in the garden for a few hours. What do you observe? You may notice tiny particles settled on its surface. So there is some tiny particles. This you can see here on its surface. You may use a magnifying glass to examine the particles more closely. This shows that dust particles are suspended in the air. They are not the integral part of the air and are considered as pollutants. They are pollutants. They are not only they are found as non-useful, but they are also sometimes considered as harmful pollutants. The nature and the number of dust particles in the air may vary from time to time and from place to place. Now we will look at this a step further. The major pollutants present in the air are particulate matter. So these are known as particulate matter, and gases like carbon monoxide, very hazardous, ozone, nitrogen dioxide, and sulfur dioxide. Nitrogen dioxide and sulfur dioxide are very poisonous. The air quality index, or the AQI, is a tool used to describe the air quality. The less A, the less the AQI is, the much better it is. Much better, much cleaner. Now let us discuss about types of mixtures. You know that the term mixture in common usage refers to the mixing of two or more components. And the components of a mixture may themselves be mixtures, so they are mixtures. As in a poha and a sprout salad, however, or pure substances like sugar or common salt dissolved in water. However, in science, all the components of a mixture must be pure substances only. So they must be pure substances. They should be only pure salt. Like if this is salt cube, it should only contain NaCl, nothing else. Mixtures could be of several types depending on the physical state of their components. Some mixtures with their examples are shown in table 8.1. Complete the third column. So let us complete this. Gas and liquid, aerated water, soda water, or oxygen dissolved in water. So we can not see both. We cannot see the aerated water, the aeration of it, or the oxygen. So I guess both of them are uniform. And then solid and gas, carbon particles in the air. So this is also uniform. We cannot see each of the carbon particles. Liquid and liquid, acetic acid and water. So this is uniform. Oil and water, no, they do not mix, so we can tell that this is non-uniform. Then solid and liquid, sand and water, sea water. So sand and water, we can see each particle, so this is non-uniform. And sea water, we cannot see salt, so we can say this is uniform. Then solid and solid, baking powder, baking soda, and tartaric acid. So we can see, no, we cannot see each of the particles, so this is uniform. And then alloys, these are also uniform, we cannot see each of them. You learned in earlier grades about the separation of mixtures. It is done to separate the components of a mixture. The examples discussed were from everyday life, where separation is done to obtain the component of interest and other components are discarded. However, in science, the purpose of separating a mixture is to obtain pure substances. What are pure substances? Have you ever noticed the word pure written on the packs of some consumables? So we can see that is pure ghee, pure milk, and pure turmeric written on the packs of some consumables such as milk, ghee, and spices. So we can see these. The word pure has a slightly different meaning in common usage and science. So this pure written here, this pure is written from, is different from what we say is pure oxygen in science. In common usage, pure means unadulterated products. So this pure ghee is not adulterated. Adulterated. Adulteration is an illegal process of adding substances which are cheaper. So for example, if there is something like a milk. Some milk is kept here, and it is very less. So sometimes people add water in it commonly. So that is also considered as adulteration. Although it is not harmful, but it is not good at all. It is usually done to increase the quantity by a lot or a product. This is usually done to increase the quantity or reduce the manufacturing cost. However, it deteriorates the quality of the product. It can also make the product hazardous to health. In science, however, a pure substance is the one that has no other substance present in it. For a scientist, even these products that look pure are considered impure if they are made of more than one substance. So, in ghee, for example, there is not only ghee, like we cannot say that this is a ghee particle that it does not exist at all. We can say that there is iron, pure iron, so we can only see iron particles. So for them, this is pure, while we can say that there is pure water, which means only water. This is water, and there is only water and nothing else. According to science, how would you classify milk, packed fruit juice, baking soda, sugar, and soil as mixture of pure substances? So milk, packed fruit juice, baking soda, and soil are impure. Sugar is pure. It contains only the glucose particles. Recall the different states of water that you studied in Curiosity grade 6. What happened was when water was cooled or heated. We observed that on cooling, water gets converted into ice, and on boiling, it gets converted into vapor. We can get back water up on heating ice or cooling water vapor. It shows that during these processes the particles of water remain the same. Now let us perform another activity in which we pass electricity through water and observe its effect. So we can see some battery, and by the way, this process that we are going to do is known as electrolysis. So we should do it in presence of teacher. Collect two small test tubes, a beaker or a glass tumbler, and a 9-volt battery. So they have taken the beaker or a glass tumbler. So I guess this is a glass tumbler, and some test tubes and a 9-volt battery. Fill 2/3 of the beaker with water and add few drops of dilute sulfuric acid to it. Fill both the small test tubes completely with the water taken from the beaker. Place a 9-volt battery inside the beaker. So we have placed the 9-volt battery in here. Without spilling the water, carefully place the water-filled test tubes on each of the terminals of the battery. So now this is also done here. Water-filled test tube placed on the terminal of the battery. So they have placed the test tubes on both of these. Wait for a few minutes to observe the formation of gas bubbles. So there will be gas bubbles forming over here, and let this continue for 10 to 15 minutes. After 10 to 15 minutes, observe the volume of gas. So here we can see there is hydrogen, and in here this is oxygen filled. So the volume is not same. By one carefully. Test these gases one by one by bringing a burning candle close to the mouth of the test tubes. What happens in each case? So this has a hydrogen, we can clearly see, because this is the double of oxygen gas, since as it is H2O. So we have two hydrogen and one oxygen. So this is oxygen and these are two hydrogen. So of course there is more hydrogen than oxygen. So now let us do the burning candle activity. So these, so by the way, these gases collected are not water vapor, not water vapor. Maintain a safe distance from this setup. So we have to maintain a safe distance. To test the gases present in the two test tubes, bring a burning candle near the mouth of each test tube. A pop sound can be heard from one, indicating the presence of hydrogen gas. So in hydrogen gas, if we take a flame nearby it, it produces a pop sound. In the other test tube, the flame of the candle will glow brighter because of oxygen. So from the above activity, we can infer that water is made of hydrogen and oxygen. When electric current is passed through water, it breaks down into hydrogen and oxygen. Is this a chemical change or a physical change? So we can see that this is a chemical change. Physical and chemical. Elements. The two substances hydrogen and oxygen formed in the activity 8.3 are pure substances and are termed as elements. Each element is made up of identical particles called atoms. So in here we can see these are considered particles, although these are not atoms. The each circle we see, the each circle in here, the each circle in here, or even here, this one spherical is known as an atom. Then two or more atoms form a molecule, so this is a molecule. Then together they form an overall substance. These particles are different from the particles of any other element. So gold, particles of gold and particles of iron will be different. So the iron one will be so the gold one will be bigger and the iron one will be smaller and the hydrogen one will be very small. So they have also different sizes. They are the building blocks of all matter. So using gold, so if many gold forms together and millions of them, millions or even billions of them form together to a gold block. Silver, sulfur, carbon, etc. The atoms of most elements cannot exist independently. So we cannot see pure hydrogen just flying in the air or somewhere because they are very reactive. Two or more such atoms combine to form a stable particles. We may not find a hydrogen individually, we may find a hydrogen along with the oxygen in water. And this is a molecule. Similarly, two atoms of oxygen combine to form one molecule of oxygen. Elements can be classified into metals and non-metals. You have already studied that gold, silver, magnesium, iron and aluminium are metals, whereas carbon, sulfur, hydrogen and oxygen are non-metals. Isn't it interesting to know that some elements like silicon and boron have intermediate properties? So they will for example, boron will follow some properties of metals and some properties of non-metals. So they are such elements are known as metalloids, which we will study later. So there are 118 elements and most of them are solid, and in out of these 118, 11 elements exist in a gaseous state at room temperature. Room temperature is considered as 25 degrees Celsius maybe, all of which are non-metals like oxygen, helium, nitrogen, etc. So these all So so many of them, all of them are non-metals like oxygen, helium, and nitrogen. Only two elements are liquid at room temperature. Mercury, which is a metal. So you may have seen mercury. It looks like a very shiny liquid, and a bromine, which is a non-metal. Although gallium and cesium are solid elements, they become liquid at 30 Celsius. So if we take these in our hand, if this is our hand and we take gallium at solid, it will become and it will look like they have melted, turned into liquid. More than 45 different elements like aluminium, copper, silicon, cobalt, lithium, gold, silver, etc. used in manufacturing a mobile phone, including its screen, battery, and other components. So all of them are used. So 45 elements are used to form a single mobile phone. Compounds. Why cannot we separate hydrogen and oxygen present in water by physical means? So we have I have shown this figure a lot. This is oxygen, and these small are hydrogen. Oxygen is larger than hydrogen. In water, the particles of hydrogen are and oxygen are so tightly attached to each other that it is generally impossible to separate them apart using physical methods. That is why water is a compound. Water is considered as a compound. Compounds are formed when different elements combine in a fixed ratio. So this is always a fixed ratio. So it is always in 2 to 1 from hydrogen. If hydrogen to oxygen, it is always in 2 to 1 ratio, because then only it will be water. The properties of compounds are different from those of elements forming that compound. So hydrogen may have different properties, oxygen may have other properties. For example, hydrogen is used as a fuel, while oxygen, you know that it is used as combustion, but together water is used for extinguisher, the constituent elements of a compound physical method. We find that are made up of two different elements, hydrogen and oxygen, combined chemically in a fixed ratio. The ratio of the number of atoms of hydrogen to oxygen has been found to be 2 is to 1. Common salt and sugar elements or compounds. So salt and sugar, they both are compounds. Sodium, a soft metal, and chlorine, a hazardous gas, combine to form a harmless yet taste enhancing substance that is essential for our lives. This substance is known as sodium chloride, which is made up of particles of sodium and chlorine in 1 to 1 ratio, which means it is if sodium is Na and chlorine is Cl, then it is NaCl, 1 to 1. So we can separate salt from water, but cannot separate sodium from salt. Now let us experiment. Put a teaspoon of sugar in a boiling tube. So we have put it in here. Heat it gently, and what do you observe? So we have heated it. As we heat the sugar, it turns brown, and then it releases also water, small droplets of water inside the boiling tube. Where did this water come from? Was it in the dry sugar? Yes, it was in the dry sugar. Since we are heating the tube, the water must have come from the dry sugar and not from the air. So it has not came from the air, it has came from the sugar itself. So after burning, charcoal is left behind. So sugar decomposes on heating and gives off carbon and water. Now let us do fifth activity. So we need to do this in a supervision of a teacher with a fume hood or a well ventilated area. Take 5.6 grams of iron fillings and 3.2 grams of sulfur powder. We have taken it here. On a watch glass, observe them carefully. Mix them thoroughly with in a watch glass. So now we have mixed this. So right now this is a mixture. Mixture. Observe it carefully. Is this a uniform or a non-uniform mixture? Can you still can you still observe both iron and sulfur as separate substances? Take half of sample in a china dish and gently heat it. So now we have heated it in a tripod stand. Under it becomes a black mass. Place this black mass on a mortar and grind it with the help of a pestle. Now we have grinded it. Now we have two samples, sample A and sample B. So now we will first let's look at their appearance. So sample A looks a bit brownish with some yellow and a black mixture, while sample B is purely brown color and texture. Magnet test. Now let's put magnet. If we put we have put magnet near this sample A, and we can see that it has become that this substance has become by a magnet. Uh, it the iron gets attracted, while magnet when attach it to this, it does nothing. It just stays there. Gas test. Take a small amount of sample A in a test tube and add a few drops of dilute hydrochloric acid. So hydrochloric acid is very harmful. Now we have added it. So now in sample A what happens? If we take it near it, it produces a pop sound which in it contains hydrogen. In sample B nothing happens. So everything was different for sample A and sample B. So while sample A was a mixture, sample B was a compound. So in compound, the sulfur and iron lost properties of both, and it has and these together create, and this compound has its own separate properties. So these are the observations that we have made here. No, they do not look the same. What sample A? Let's answer these. No. Which sample A? Let's write here sample A. Can we separate components of sample A and B? Yes for sample A and no for B. Do gases evolve in both samples? No, only in A. In both cases, do gases smell the same or different? We can say that sample A is a mixture, while sample B is not a mixture. So iron plus the hydrochloric acid forms hydrogen gas. That is why we got the pop sound. Sample B, when we do nothing, it just forms iron chloride with hydrogen sulfide, so it's nothing special. Then now the next is, how do we use elements, compounds and mixtures? Elements, compounds and mixtures are all around us. The air we breathe is a mixture of gases like oxygen, nitrogen and carbon dioxide, as we all know. Water which is essential for life, is a compound made of elements, hydrogen and oxygen. Elements like iron and aluminium are used to construct bridges. Iron and aluminium are used to form bridges, buildings and vehicles. Understanding these concepts is not about recognizing what surrounds us, is also key to innovation. For instance, a chemist studies how elements combine to create compounds, enabling them to invent life-saving medicines. So, what do chemists do? They take different elements, form different compounds, then check their properties, and then create new medicines. Thereby, so this knowledge also helped in the creation of fertilizers, enhancing crop production that feeds the ever increasing human population globally. Engineers and material scientists rely on their understanding of compounds and mixtures to design materials with unique properties. For example, they have developed alloys like stainless steel. So, after we have developed stainless steel, which is very strong than iron. Wood, steel, and concrete are mixtures. Now let's discuss this. Aerogel, wonder material developed by material scientists. Graphene aerogel. This is aerogel. It is the lightest material on earth and made from carbon. It is so light that even grass can hold it. It is highly porous and therefore has a high absorbing capacity. It can absorb lots of things. That is why it is also used as an environmental cleaner to clean up oil spills in both seas and on land. It is used for fabricating energy saving devices and special coating for building. So it is used as special coating for bridges, for buildings. What are minerals? Most rocks are a mixture of minerals which can be viewed with the eyes or by using the magnifying glass. So these are minerals: quartz, calcite, mica, pyroxene, and talc. Now the minerals are called native minerals, which are pure elements and not compounds. These can be such as gold, silver, copper. These are these are minerals and they are elements. Or non-metals like sulfur, carbon, they are also elements. Most of the minerals are compounds made of more than one element. Some common examples of minerals include quartz, calcite, mica, pyroxene, and olivine. Olivine. Many things that we use in our everyday life are made up of minerals or elements extracted from minerals. For example, cement is made from calcite, quartz, alumina, and iron oxide. So it is made from many things and it is strong. And talcum powder is made from mineral talc. Our scientific heritage. Use of elements, compounds, and mixtures in Indian art. The Dhokra art is a craft from Bihar and Odisha that uses different metals to create beautiful figures inspired by nature. The process begins with shaping a design in beeswax. So what they do that they first mold a design like this that in beeswax, and then they form a mold over it by putting wax all over it. Then after the clay is hardened, they remove the wax by melting it, by burning it, leaving a hollow space. Then this space gets filled with molten brass. Then this space gets filled with molten brass, and then that also gets when it freezes, kind of becomes solid. It shows a shiny golden color like shown here. The figures often show animals, people, and nature, reflecting tribal creativity and tradition. Elements and compounds are the building blocks of, of matter. Everything that has mass and takes up space is matter. They make the materials we see and use every day. However, not everything around is matter. Light, not matter, not matter. Heat, heat is basically just vibration. When objects get more hot, they just vibrate more rigorously. and they become hot. Of the constituent particles or the atoms just vibrate more rigorously and they become heat. Electricity is just the flow of electrons, so we cannot say that this is a matter. And thoughts and emotions, they are also not matter. So for example, we cannot hold like, so you cannot go to a friend and say, look, I have a cube of sadness. No, that is not possible. Understanding what matter is and what is not helps us better understand the world around us. And that is the end of the chapter. Thanks.